Okay, good morning, everybody. Welcome to Papa Lim Physics Classroom. Okay, today we'll be reviewing Holy Innocent High School paper 1, okay, for science physics. Okay, same as before, I will review some of the interesting questions that appear in the paper. And if you have done it, you may want to take a look and to make sure that you are on the answer is correct and you make sure you are on the right track. Okay, without delaying, okay, I will start the sharing now. Now, for this particular paper, same as before, I have included the answer here. So if you have done your paper, you may want to pause now, okay, to actually check the answer to see which questions you have gone wrong or which question you have done well. Okay, if not, okay, I have actually highlighted some of the interesting questions here that you may want to take note, or all the 8 questions. These 8 questions here are actually some of the, I would say, higher order thinking, or maybe some of the interesting questions that don't really come out in some of the past paper that I see. Okay, same as before. If you have not done this paper and you are interested in doing it, okay, I leave the paper in my Google Drive and the links at the description panel there. Okay, so you by all means go ahead and try out the paper. Okay, this is definitely a good paper. That's definitely worth your time. Now, without delaying, okay, let's start with question 1 now. Now, for question one here refer to ticker tape timer. Now, for ticker tape timer, the important thing here is this. For ticker tape timer, the important thing is this 50 dots per second. Now, this information actually tell us the time for 50 dots in 1 second. This will give us 1 dot is actually 0.02 seconds. This information will actually tell us that the time taken to make 1 dot is 0.02 seconds, which means that actually the time taken to stamp these dots, this particular dot, is actually 0.02 seconds. And then after that, I stamp this dot, another 0.02 seconds. So another dot, 0.02 seconds. Okay, so in fact that for me, based on the picture, for me to stamp the 4 dots, the extra 4 dots, I actually need a total of 4 times 0.02 second, which is 0.08 seconds. So this is the time taken for me to stamp the 4 dots from S to T. Now, the other one that we look at is the distance traveled. Okay, distance traveled for S to T will be 7 plus 9 plus 11 plus 13. So the total distance you have will actually be 40 cm, sorry. Okay, so if I have the total distance, if I have the total time, and if I want to calculate average speeds, okay, so I just need to calculate the total distance by total time, which is 40 cm divided by 0.08. Okay, and take note, the option here all are in meter. So my 40 cm, I need to take note, I need to divide by 100 to convert it back to meter first. Find your answer to be B. Okay, for ticker tape timer here, I would say ticker tape timer nowadays, I usually don't see this type of question appearing, but nonetheless, it's something that is worth investigating. Okay, especially the fact that ticker tape timer, it usually have this tendency to tell us this information. So students must know how to make use of this particular information to derive this 1 dot is 0.02 seconds. Because only with this first step, you will allow the students to actually calculate the total time. And then with total distance, you will be able to find the average speed of the particular object here. Distance-wise, usually most of the students, they are able to find. It's the time that you must be careful. Question 2. Question 2 here, we're looking at the free fall. Now, but free fall here, there's a certain condition. It's free fall through vacuum. Now, when an object goes through vacuum, one of the important field characteristic is this. Your acceleration will actually be 10 meters per second squared, and this will be constant. Okay, for vacuum, this will be constant. You will keep increasing. Your acceleration will be the same. And after that, what happened? Your speed will keep increasing. So that's why my option will be B here straight away. Now, take note, for non-vacuum, there's a few characteristics. Initially, it's the same. Initially, you'll find that A is actually 10 meters per second squared. Okay, your V is increasing. Then after that, what will happen is that your acceleration will actually decrease and it will actually become 0 here. Okay, so when you take decrease, remember your acceleration is decreasing at this point in time, okay, your velocity is actually still increasing, but your increment is actually getting slower and slower. And when your acceleration hits 0, this is what we mean by constant speed now. This is what we call constant speed, or sometimes we call this maximum speed. Okay, or what we know as terminal velocity. Okay, so for free fall. Free fall, there are two situations. One is vacuum. Vacuum is really more straightforward in the sense that the constant acceleration will be constant, the speed is always increasing. But when you have free fall with non-vacuum, meaning with air resistance, you need to take note of the changes. Okay, they will be considered two parts. One will be the initial phase, whereby the A is constant, velocity is increasing. Then after that, you have the second phase, whereby your acceleration will start decreasing. And acceleration decreasing, at this point in time, your velocity is still increasing, but it's just increasing at a slower rate, but it's still increasing. Then after that, eventually you end off with acceleration, you will decrease till zero. And that's whereby your velocity actually remains the same and you will not increase anymore. Okay, it will stay constant. And that's what we mean by terminal velocity, or what we call maximum velocity. Now, question 4. Question 4 is a classic example. The important thing to take note is actually the wheel that is driven by the engine. Now, for car, there are two sets of wheels, front and back. Okay, and usually let's say in most of the car, you have a front wheel driven, which means the wheel that is in front is actually driven by the engine. And when you have engine, you will have this particular situation. When it's driven by the engine, okay, so when I turn this way, the wheel turn this way. Okay, if it's driven by the engine, so this is by the engine, or what we call your front wheel. Okay, when it's driven by front wheel, you have what we known as your Newton. You take note of where the wheel is turning and where the force is exerted, or where the friction is exerted. In this case, when the wheel is turning, the wheel is actually pushing the floor away. Okay, so let's say in this case, we follow the question, the wheel is going, the direction is going this way. The car is going this way. So now the wheel is turning clockwise, and because of that, the wheel is actually pushing the floor to the left-hand side. So this is the force by the wheel. There's that force on the floor by wheel. Based on Newton's third law, the same force, the same magnetic force will be exerted onto the wheel itself by opposite direction. So this is this way. So this will be the force exerted on the wheel by the floor itself. And this is the force that will actually cause or actually propel the car forwards in the direction that you want, the traveling direction. So if you are looking at the front wheel, where it's driven by the engine and the front wheel is going to the right, you'll find that the friction exerted on the wheel is actually to the right, or this is what we call forward friction. Okay, on the other hand, if you have the back wheel, it is the floor. And you'll find that the wheel is going the same direction to the right. Okay, you'll find that the friction that you're looking at on the wheel is not driven by the engine. The wheel is being dragged. So when you drag along the floor, you'll find that the force on the wheel is actually backwards. Okay, because now the wheel is being dragged through the floor itself. So when it's being dragged through, the friction is actually at the back, which is against the motion. So in this case, this friction here is what we know as a backward friction. It actually opposes the motion for the wheel on the back. For the wheel on the front, okay, this is what we know as a forward friction. Okay, so depending on the question, so sometimes the question will give you the back wheel, sometimes the question will give you the front wheel. So you must know which wheel we are looking at. And how do we differentiate which wheel? Is the fact that the question will say driven by the engine. Okay, the one that's driven by the engine will experience what we call the forward friction. So that's why I know if the wheel is going this direction, and if the wheel is driven by the engine, the friction will be the same direction as the direction of travel, which is what we call forward friction. Okay, so students, you have to take note of these two type of particular location. That's why some students will say, hey, how come the wheel on certain question is the friction is actually on the opposite direction, and sometimes on the other question, the friction is actually on the same direction as the travel. Okay, the important thing is to differentiate which wheel we are looking at, whether it's a forward wheel driven by engine or is it the wheel not driven by engine. Now for question 8 is the kinetic particle model method. Okay, the balloon is squeezed. Okay, pressure is increased. Okay, remember, so the number of particle remain the same. It's being squeezed. Okay, so number of particle being squeezed. When I say squeeze means what? Okay, space becomes smaller. Okay, so what we call the volume becomes smaller. So now when I have a big balloon, I squeeze it to become a small balloon now. Take note, the particle is the same. The number of particle is all the same. The number of particle here, again, number of particle here is all the same. Again, number of particle here is the same. Okay, so number of particle never change. Okay, but what happened is now because I have a smaller space now. Okay, so now with a smaller space, the particle inside actually has a smaller space to move. And what happens is actually it will collide more often. It will definitely collide more often. Because why? Because with a smaller space, I have the same particle, same number of molecules, same number of molecules, smaller space definitely is more crowded there. Okay, so now it's become more crowded, and as a result, you will actually collide more often. But here, take notes. The question is, you will collide more often on the between the particles and also on the wall itself. Okay, and the question says that I want the increase in pressure. I want the increase in pressure. This is why in the balloon. So the collision I'm looking at is where? The collision is between the balloon on the balloon itself. Okay, so the collision between the balloon is what caused the pressure on the balloon itself. When the particle collide more often, yes, I have the collision between the particles. I also have between particles and wall. So if I want to know the pressure on the balloon itself, pressure of the balloon itself, I definitely want the force exerted between the particles and the wall. But this is what gives rise to the balloon in the pressure. So that's why these words is actually important. Okay, so when we talk about collisions, okay, it's not just that, well, the moment I have a collision, I definitely choose the answer here. No, you must be precise. The question is talking about the pressure in the balloon itself, on the balloon itself. So that's why I need the wall of the balloon. So that's why answer D is more, answer the question is more relevant to the context. That's why the answer D is actually correct with reference to the context. Okay, so that's why for students who are doing the MCQ question, you have to read the question carefully. But be it paper 1, paper 2, you have to read the question carefully. You must be precise, you must be concise, you must know what the question is asking for. Now for 11, we're looking at the ether. Okay, one of the things that you have to take note, ether is it's like alcohol. It's alcohol actually. It has low boiling point, or aka it evaporates very fast. So it evaporates at how fast? It evaporates at room temperature. So even at room temperature, you have this, it will evaporate very fast. That's why alcohol, salt, all these things, you will find that you have this cooling sensation. Okay, when ether evaporates, what it does is you will actually absorb energy from the water. Okay, so you will actually cool down the water. You cool the water. Okay, and when the ether evaporates, it cool down the water by a lot. Eventually, you will hit very close to the freezing point, and that's why the layer of water will actually become ice. It will become a thin layer of ice due to ether. That's why this where the cooling effect come in. Okay, so that's why my answer here is actually A. Absorb the water energy from the water. Okay, so just take note of this. Now, for question 14 here, it talk about lenses, and for this particular question, you have to take note of the 6 diagram. And which of the 6 diagram are we using at? So you have to look at the question to sieve out. First one is the orientation. Okay, the image and object, they are opposite of each other with the lens in between, which means this will tell us a clue that the image is real. Second, the height of the image, or the size of the image versus the object. The image is smaller, so which means this will be diminished. Okay, real and diminished. Okay, so it will mean that if it's real and diminished, it will mean that the object, how far is the object? Based on the picture, for real and diminished object, the object has to be more than 2f. And for the object to be more than 2f, this is the first condition. Okay, and the second condition is where? The image must be between f and 2f. Okay, so this is how you sieve out this particular location. Because how do I know it has these 2 conditions? Because firstly, I will know that it has to be diminished and it has to be real. And if you look at your 6 diagram, you'll find that the one that support real image, real, diminish. The condition is the object must be more than 2f and the image must be between f and 2f. So which means that automatically you will know that B is out. B, the object distance and the image distance is roughly the same. If it's object distance same, okay, object distance, image distance same, the image that I should get, it should be the same size. Okay, but now this is diminished. So that's why I know B is out. And secondly, if I choose A won't be the answer, because if you choose A, you'll find that my object is actually nearer to the lens. But based on condition 1 and condition 2, my object should be further away from the lens as compared to the image. The image should be nearer. So that's why option A is out. You only leave us to option C and D. C and D will satisfy the condition whereby the object is actually further away compared to the image. But I will not choose D, because if D is more than 2F, if I choose D, the image object distance is definitely more than 2F. But what happened to the image? The image is very near to the lens, and this will give rise to the fact that it will not be more than F. It will not be in between F and 2F. Definitely will not want. So that's why if I know A, B, and D, the only answer here I will left will be C. And true enough, you test the answer here, you'll find that if this is the image object distance, which is more than 2F, it is possible that this distance is definitely within, is slightly more than F, but less than 2F. So that's why C is the option that is possible to encompass these two conditions. So that's why C will be a better option as compared to D. Okay, for lenses, it's important that students that you need to know all the 6 diagrams, all the 6 possible scenarios by heart, and know what are the changes accordingly. So because some of the questions really, I don't need you to draw, but I need you to deduce the characteristics of the 6 diagram, or one of the 6 diagram, or even could be the characteristic of the object distance, or the image distance, like what this question did. Okay, so the 6 diagram is utmost important. Now, for question 19, okay, for question 19, we look at multi-plug. Okay, the most obvious thing with multi-plug. The moment you see multi-plug, you know that one of the fault that associated with multi-plug is what we know as your overloading. Okay, and remember, for overloading, the moment you see overloading, one of the main thing that hits you straight away or hit me straight away is that what we know as your current in main cable. So now for overloading, let's take a look. If this is my power source, okay, so this is my component. For overloading, remember, for overloading, okay, the current flowing through each component, the current is actually the ideal current, the calculated current, the desired current. The current flowing through each of the components is the ideal current. So this current is the ideal current, is what is meant to flow through the object, okay, the components. But for overloading, what happened is the risk is not on the component, the risk is on the main cable. Because in order for the power source to supply all the current to the components, a large current must come up from the source. And this is what we mean by the current in the main cable. This current that flows through the main cable actually is very large, because the moment the main current from the main cable reaches the nodes, the junction, the current will actually split to give the correct amount to each of the components. So which means that the IT at this point, the current in the main cable is actually very high. So that's why this is one of the reasons why when you talk about overloading, the current in the main cable is the one that you're concerned, because this is where the fire or the electrical fire will take place. Because the main cable is very high, the current in the main cable is very high, the temperature in the main cable is very high also. And as a result, the main cable will most likely to catch fire first. Okay, when you look at overloading. So that's why for this type of question, for overloading, the main thing you look at the question is to check, is there a mention of the main cable? But that's where it will give rise to the fire. Okay, it's not because of the voltage. It's not because the current of each device is high. Okay, make multi-plug. Okay, each of the components have the correct current for themselves. When if it is the correct current for each of the component should actually function normally. So for overloading, the only possible reason there's a hazard is because of the current in the main cable. It's actually very high, and it actually will cause fire in that data. So that's one that we always need to take note. Even at home, we try not to actually plug too much plug in the in the model in the adapter. Okay, if it's possible, okay, transfer them to different sockets so that it even out the load, prevent the cable in the main cable, prevent the temperature in the main cable from rising. Okay, so take note of it. Now the last question here is X. Question 20, you deal with your the current and the magnetic field strength. Now, if you look at the magnetic field lines, you look at the magnetic field current X and Y. Let's take a look at X first. Now, X cable, for example, if X, okay, current X can be either going in or it can be coming out. Okay, how do we know? Okay, so that's where we use Maxwell rule to decide whether it's in or out. Okay, but one thing for sure is this. Whenever I have a current, I definitely have a magnetic field lines. So for example, the magnetic field line is this way for X. And based on the concept of compass, okay, compass and the magnetic field lines, they are actually the same direction. So which means that if my compass P point down, I will know that the magnetic field line at P is actually pointing down. If right side is pointing down, means my left side here will be going up. So which means that the current in X will generate a field line that is clockwise. And if you look at our Maxwell right-hand rule, the current that will generate a clockwise magnetic field line means that the current must be going inwards, okay, which is the X. The current at X has to be into the paper. Because current into the paper, you will generate a clockwise direction field line, which is what denoted by P. If I apply the same thing to Y, okay, same thing, Y will generate a field line, okay, when the current flow. Okay, so you take a look for R, which is near to Y, the field line, the magnetic field line is going upwards, okay, denoted by the compass direction. So which means the field line is up and the field line is down here. So which means the magnetic field line generated by current Y is actually clockwise also. Okay, so which means that for me to generate a field line that is clockwise, it means that the current direction for at Y, it has to be X also, going into the paper. So in fact, if you look at these two situations, you'll find that actually X and Y, the current direction is actually the same, which is going into the paper itself. So which means that option A and option B is out already. Now, same thing is what happened to your Q. Okay, for Q, you'll find that there is an intersection, there's an overlapping of the current, overlapping of magnetic field lines. For example, for X, with respect to X, wire X, the field line due to X, which is the purple one, would be this direction. This is field line due to X. On the other hand, field line due to Y, magnetic field line due to Y, okay, the Y is going in, okay, is clockwise. Field line due to Y, which is denoted by the green color one, is going upwards here. Okay, so you find that at Q, there's an overlapping of magnetic field lines. Purple one, which is downwards, green color, which is upwards, happening at Q at the same time. And based on the compass, and the compass will tell me the final direction of the field line. And based on the compass, you find that the direction of the compass here is actually pointing upwards. So which means you will tell me that the fact that the green color magnetic field line will actually be stronger than the purple one, because the final direction is upwards. So this will tell me that since Y is actually stronger than, green is stronger than purple, or to be exact, Q final direction is upwards, it will denote that the magnetic field line by Y, the green color one, is actually stronger than the purple one. And which means that my current in Y must be larger than X, so that the field line by Y, which is the green color one, will actually be stronger than X, so that eventually at Q, the current direction is still upwards, it's still the follow the direction of the magnetic field line by Y. So which means that this answer here will also be C here. Okay, so this question here, it will require the student to actually analyze what's the field line at P and R first. Okay, once you analyze the field line direction at P, you will know that, the field line at P and R, you will know that X and Y actually have the same direction, current has the same direction. And after that, you proceed on to analyze the field line at Q. Once you know that Q, okay, the final direction of Q is denoted by the compass, which is upwards, you'll find that the field line, overall field line that stays at Q actually is the field line that is from Y. So that's why if for the overall field line at Q to be Y, it means that the current size of current at Y is definitely bigger than the current at X. Okay, we have come to the end of this video. I do hope the video is useful for you. At least it might have actually made your learning of physics much more enjoyable and easier along the way. Okay, if not, okay, stay tuned for my next video. Bye-bye.